Welcome to Module 12, where we'll be investigating axiomatic set theory. So we'll use our first order logic apparatus to start modeling naive set theory, or finish modeling naive set theory. And then at the end of the video, we'll introduce the notion of a mathematical structure, which is the first order analog of a truth table for propositional logic. So this is sort of what we'll need in order to state the completeness theorem and the soundness theorem for first order logic in our next module. So as usual, we have some learning objectives for this module. The first is to apply axiomatic set theory. So we'll finish off the process of formalizing naive set theory. Last module, we talked about the axiom of extension, the axiom of comprehension, why it was inconsistent, and then we started introducing the notion of the separation axiom. In addition to that, we'll start introducing some of the axioms related to basic set operations like the power set, union, intersection, and replacement. And the homework assignment for this module has some excellent examples where you're asked to take a set sort of listed with its elements listed and then apply some of these operations. Learning objective 3 and 4 are related to one another. Remember, the axiom of extension tells you that you can show two sets are identical if they have the exact same elements. And that usually consists of sort of a two-part proof, right? Or like in one case, you show that like given an element of one of the sets, it's in the other, and then you go sort of vice versa. And those two parts lead to the notion of a subset. So we'll sort of make that a bit more concrete, and then we'll talk about how you can show one set is a subset of another. And we'll need that as we talk about the operation of power set as well. Now, the whole thing is all leading up to the notion of a first order structure, or basically a mathematical structure. And the reason we need to sort of talk about set theory first, are defined in terms of sets. And they'll be our sort of analog of truth tables for this first order logic that we'll be looking at. And we'll need them in our next video when we talk about the completeness theorem for first order logic. So just a reminder of what we had talked about last week when we were starting to solidify or formalize naive set theory. The axiom of extension, which was sort of one of these fundamental axioms of set theory, was that two sets were identical if they have the exact same elements. And we wrote that out in first order logic down there in green. I'll remind you that since the language of set theory doesn't have any constant symbols, A, B, and X are considered variables here. And so that's why you're seeing things like for all A and for all B. And we're following the convention that we're using A, B, and C sort of letters from the beginning part of the alphabet to indicate sets, and then X, Y, and Z for elements. Although in set theory, everything is really a set, and so they really range over just sets. Now, one thing we didn't talk about last time was the notion of the subset relation, and it's sort of like built into this highlighted green sentence, and we can sort of rewrite it in terms of this relation. So we'll write this A and then this sort of sideways U, read as the subset relation, B, for shorthand for the following universally quantified statement. For all X, if X is an element of A, then X is an element of B. So all of the elements of A are elements of B. And instead of writing out that universally quantified statement, we just typically write it as A, the subset relation, and then B. Now, the subset relation is not going to officially be part of the language of set theory. It's just an abbreviation. But it does allow us to express some of our statements a little more succinctly. So, for example, down here on the bottom, you'll see that I've replaced that biconditional in the axiom of extension with just a conjunction of two subsets. So to show that two sets have the same elements, you just show that A is a subset of B and B is a subset of A. So everything in A is in B and everything in B is in A. And we'll conclude that they're the same. Now, this is typically the format that most sort of mathematics students have been introduced to the notion of subsets and the axiom of extension, although they probably didn't necessarily call it the axiom of extension when it was first introduced. Okay, so that's the idea of a subset. And notice that to prove something is a subset, you use the method of general conditional proof. You take an arbitrary x and A, you use sort of what the meaning of being an A is to then show that you have to be also a member of B. You close off your subproof and you are able to make the universal introduction and conclude that for all x, if x is in A, then x is in B. Okay, so that was the axiom of extension, and nothing controversial about it. It doesn't lead to any inconsistencies. So in naive set theory, any collection of objects is allowed to be a set. However, one can run into contradictions fairly quickly if you allow for just collecting together any old objects based on some sort of formula. And in particular, we saw a well-formed formula with a free variable of x that led to basically a contradiction when we assumed this axiom of comprehension. We called that Russell's paradox. And what it meant was that we really couldn't use, or we couldn't assume comprehension as an axiom, because our principle of explosion would tell us that if we reason to a contradiction, we could then obtain any sentence at all. And so this would be sort of a very useless axiom for us to adopt into our system. So what happens is that instead we try to adopt some of the consequences of the axiom of comprehension that allow us to avoid the inconsistency from Russell's paradox. And last module, we gave an example of that, where we modified the axiom of comprehension to this axiom of separation. And here it says axiom schema of comprehension and axiom schema of separation, because really there's one axiom for every well-formed formula with a free variable of x. And that's what's said in this sort of box here on the bottom left. So given a set A in a well-formed formula, P of x, with that free variable x, there exists a set B consisting of those elements in A that satisfy the well-formed formula P of x. That is, this B is equal to this set builder notation, the set of all A's, such that P of x is actually a set. So there in gray, the axiom of separation is sort of saying that that set B really is a set that we can then reason about and assume exists. We use these in mathematics all the time, and just as a reminder, that sort of set builder notation you're seeing there in that gray box is typically what's used in mathematics. However, again, just like in our sort of previous side with the subset relation, it's not officially part of the first order language of set theory. So instead, we had to write out this axiom schema of comprehension a little more carefully. Okay, before we go on to introduce some more axioms, let's see a nice application of the separation axiom in order to prove the existence of the intersection of two sets. We'll be using this new symbol, which looks like an upside down U, to represent the intersection. It's not officially part of our language of set theory here, but we'll be using it just sort of as an abbreviation for the following set. So suppose you're given two sets A and B. Then by separation, for example, the formula X is an element of B is a well-formed formula with a free variable of X. So you're then free by separation to form the elements in A, which satisfy that formula, or in other words, the elements in A, which are also in B. And that's exactly the overlap of the two sets. And you can see that highlighted in red here on the right. And basically, the idea is that the intersection sort of separates A into two parts. And so we just need a formula for that red part of A, and it's given by X is an element of B. Okay, so that's one of our basic set operations, and we don't really need an axiom for that intersection because it arises as an instance of the separation schema. So now we'll introduce some axioms related to some set operations. These can't be obtained from the separation axiom because they're not parts of a larger set, but instead, if you're handed some sets, they allow you to construct some different types of sets. The first is called the pairing axiom, and the second is called the union axiom. Later, we'll see the pairing axiom is used to construct ordered pairs, like you might see in the Cartesian plane or the xy plane. And the union axiom is used to construct the union of two sets, similar to what we saw with that Venn diagram for the intersection, but now sort of either in A or in B. Now, we could have constructed both of these from the comprehension axiom, but as a reminder, the comprehension axiom is inconsistent. So these are sort of two instantiations of what we might have gotten from the comprehension axiom. And the textbook does a great job of sort of drawing this detail out. We're not going to go back through some of that information, but here we'll just sort of state it in its English form. And then here in green, you can see it in its first order logic form. So that pairing axiom says for every x and for every y, there exists a set A such that for every element z, z is in A if and only if either z is equal to x or z is equal to y. In other words, this set A that it's asserting to exist is exactly the pair set consisting of the elements x and y, and that's a set with just two elements in it. Now, the union axiom is a bit odd on first glance because it doesn't quite say exactly that the union of two sets is a set. Instead, it says something a little bit stronger. Here it says that the union of all the elements of a set is again a set. And you have to remember that in set theory, everything is a set. So if you're handed a set, the elements of it really are just sets. And here the union axiom says you can form the union of all of them. And that may be an infinite union if the set you were looking at was infinite. Now, in first order logic, it says essentially the following down there in green. For every set A, there exists a set B such that for every element x is in B, so the elements of B are exactly and precisely those, if and only if, there exists some C such that x is in C and C is in A, so that you're a member of a member. And we'll see that in our next slide and how it's used to construct the union of just two sets. You have to use both the union axiom and the pairing axiom in conjunction with one another to get the union of two sets. Okay, so again, these are axioms that assert the existence of a set given some other sets. Okay, so how do we form the union of two sets? And I'll just remind you that the Venn diagram you're seeing here in sort of purple is the Venn diagram for the union of two sets A and B. And basically what happens is, well, maybe they overlap a little bit, but the union is anything that's in A or anything that's in B. So you shade in sort of both of those. And here we'll use basically a big U to denote the union, and we'll call that the union symbol. Again, just like the intersection, it's not going to be an official part of the first order language of set theory, but just a convenience for denoting the set that we're looking at here. Now, in order to actually form the union, you first have to form the pair set consisting of just the set A and B. So you use the pair set first, or the pair axiom first, to form that two-element set. Now, that two-element set only has two things in it, and it's certainly not the union of A and B. And then you apply the union axiom to that pair set. And remember what the union axiom said. It said that the union of the elements of a set is again a set. And here the elements of this pair set are just A and B. So the union of the two of them, A union B, is again a set. Okay, so you have to actually use both the pairing axiom and the union axiom to get the union of two sets. But notice that if you had an infinite set instead of just a pair set like AB, then you could potentially take the union over infinitely many sets. And that's the reason why they're separated out the way they are, as opposed to just saying the union of two sets is a set. The next axiom we look at is the power set axiom. If a set A is given, then the collection of all subsets of A is again a set. Now, this is a consequence of the axiom of comprehension when we take our well-formed formula to be X is a subset of A, as sort of written out there in set builder notation on that third line down. The green sentence highlighted in this slide is the first order version of the axiom. For every set A, there exists a set B, such that for all elements X, X is in B, or a member of B, if and only if X is actually a subset of A. And again, this subset is just a shorthand for all Z. Z is an element of X, implies Z is an element of A. Okay, so just as a nice example of applying the power set operation, we have on the bottom here the power set of the set 1, 2. And in this case, the set 1, 2 just consists of a set containing two elements, namely 1 and 2. This set has four possible subsets, the first being the empty set, the second being the singleton containing 1, so the set containing just 1. There's the singleton containing 2, so the set just containing 2. And then finally, there's the full set itself, the pair set containing both 1 and 2. And those are listed there on the bottom, on the right-hand side. And you just go through and compute all the different possible ways of omitting some of the elements from the given set that you're looking at. Okay, so if you look carefully at the format of all of our previous axioms, they assert that given a set, you can produce a new set. For example, from two sets A and B, you can produce the intersection or the union. At no point do they actually assert the existence of a set. The axiom of infinity, which we'll look at now, is the first axiom that actually asserts the existence of some set. However, before we state it, we'll need a bit of notation. First off, something you don't see on this slide is the definition of what's called the empty set. The empty set is just the set containing no elements at all, and by extension, it's a unique set. Now, an inductive set, which we'll use capital I here to denote that set, is said to be inductive if it contains the empty set, so the empty set has to be contained within I, and for any set X that's in this set I, X union the singleton X is also a member of I. And this allows us to build up more and more and more sort of elements of this set I. And because of this sort of building up of elements, the set I will be an infinite set. Now, the axiom of infinity is simply the assertion that there exists some inductive set. This then allows one to introduce or define the set of natural numbers to just simply be the smallest inductive set. And the smallest inductive set would just be the intersection of all possible inductive sets. And we saw that in our last module at the very last slide when we introduced the definition of the ordinal numbers. So 0, 1, 2, 3, 4, and so on and so forth. And we saw that this X union, the singleton, was the successor operation along those ordinal numbers. So we're now going to move on to the last three axioms for set theory. And what we'll find is that they're a bit more technical than the previous ones, in the sense that they were adopted in order to carry out certain constructions and to avoid certain contradictions. Now, we previously have talked about the axiom of separation and how we adopted the axiom of separation to avoid some of the inconsistencies in the comprehension axiom. But in order to actually avoid the Russell paradox, we, in addition to the separation axiom, will also need what's called the axiom of regularity. Now, the axiom of regularity says that every non-empty set contains an element which is disjoint from the set. And disjoint here just means that the intersection with the set is empty. Okay, so in green there, I've highlighted the formal sentence. And here we're using for the first time the symbol for the empty set. It's a circle with a slash through it. Just like some of our other symbols that we've introduced, it is not part of the first order language of set theory, but we will use it here for convenience. Recall that the empty set is the set consisting of no elements. Okay, so what does that sentence in green say? It says that for every set A, if A is not equal to the empty set, in other words, it's not empty, then there exists an element X, which is in A, and the intersection of X and A is equal to the empty set. In other words, every non-empty set contains an element which is disjoint from itself. Now, the corollary that we'll need, and there's a whole lot of interesting consequences of the axiom of regularity, but the corollary that we'll need to show that Russell's paradox can be avoided is the one that you're seeing here below that green highlighted sentence. And it's the result that no set contains itself. Okay, so let's see what the proof looks like. Let's suppose that we have a set, A, so that's just an arbitrary set. Then by the pair axiom, we can form the singleton containing A, and that's a non-empty set because it contains exactly one element. Now, by this axiom of regularity, that one element set has to contain an element which is disjoint from itself. In other words, A intersect the singleton set containing A is empty. And in particular, if that intersection is empty, then A cannot be an element of itself. In other words, the negation of A is an element of A is true. Okay, so let's now see on our next slide how we can avoid the Russell paradox using this result. Let's now come back and see how we can resolve Russell's paradox. If we form the Russell set now in ZF, remember, we're not assuming the comprehension axiom anymore, but if we form it in ZF, then what we'll need to use is the separation axiom. And the separation axiom requires that we start with a set. In this case, we'll start with the set A, and we'll look at all of those elements which are not members of themselves. Now, by our previous slide and the axiom of regularity, we know that no set is an element of itself, and therefore this collection just consists of exactly all of the elements of A. Now, by the extension axiom, that means that this collection is equal to the set A. And here we know that, again, by our previous result, A is not an element of A. And so there is no contradiction and there's no paradox that we obtain when we try to use this well-formed formula that was identified by Russell and which gave an inconsistency when applied to the axiom of comprehension. So here the axiom of regularity and separation sort of come to the rescue and help us avoid that paradox of Russell's. The last axiom that we adopt for ZF is called the replacement axiom. And just like separation, it turns out that it's actually an axiom schema. So for every well-formed formula P of xy, we'll get an instance of this particular axiom. Now, the axiom basically says that if you can define a function using this formula P of xy, in other words, for every x in some set A, there exists a unique y. That's what that exclamation point there means next to the existential quantifier, that there exists a unique y that satisfies P of xy. Then you can basically form this set that you see down at the bottom, which consists of the range of that particular function. Here, I'm not going to say much more than that, and I'm not even going to formalize it into first order logic because we really won't have any use for it. Again, it's one of these technical axioms that allows you to do some constructions with cardinal numbers and ordinal numbers that are necessary in order to get set theory to work. But in our current context, and for what we'll need it for in the completeness and incompleteness theorems, the replacement axiom won't appear. Nonetheless, it's still part of ZF, and so we'll include it in this slide. So let's just summarize the ZF axioms and then say a bit about another additional axiom, which is sometimes referred to as the axiom of choice or Zorn's lemma. First, we had the extension axiom telling us when two sets were identical. And recall that that means that they have the exact same elements. We then weakened the comprehension axiom to get a whole series of axioms that allowed us to construct and build sets. For example, we had the axiom schema of separation, which said that if we had a well-formed formula and a set, we could use that well-formed formula to sort of split the set in half and find those elements which satisfied the well-formed formula within the set. And then we had a series of axioms related to some operations where if you were handed some sets, you could then form some new sets. And we introduced the pair axiom, the union axiom, and the power set axiom. We also talked a bit about the intersection of two sets, but saw that that was an instance of the separation axiom. We then looked at the axiom schema of replacement and the regularity axiom. And we saw that both of those were a bit more technical. And in particular, the regularity axiom allowed us with the separation axiom to avoid Russell's paradox. And recall that Russell's paradox is the reason why we couldn't adopt the comprehension axiom from the very beginning. Okay, so those axioms together are typically referred to as ZF, or Zermelo-Fraenkel set theory. Sometimes you'll also hear the term ZFC axioms. The C stands for what's called the axiom of choice. And the axiom of choice just says that if you have a non-empty set, then there is some set C that contains exactly one element from each element of A. In other words, it chooses out one element from each element of A, and the set C is called sort of the choice function or the choice set. That axiom happens to be sort of independent of the other ones, so you can't prove the axiom of choice from the others. And the axiom of choice itself is used heavily in mathematics. So often in analysis and algebra, the axiom of choice is used to show the existence of certain objects or certain types of structures. It also has a series of very strange and unusual sort of consequences. For example, the Banach-Tarski paradox is a consequence of the axiom of choice. And if you've never heard of it, it's a fun one to maybe Google and read up or watch maybe a video or two about it. But that is the first order foundation for axiomatic set theory. Now that we have axiomatic set theory sort of solidified, we'll now look at some applications. And the main application that we'll be interested in is introducing the notion of a first order structure, which will be necessary in the statement and proof of the completeness and soundness theorem for first order logic. Before we say a bit about the definition of first order structure, we'll need to say how we can represent relations via ordered pairs. Now, we've talked about the pair axiom and how we can form the pair set XY. However, when we do that, it's an unordered pair because the axiom of extension would tell us that the set XY is the same thing as the set YX because the order doesn't matter. On the other hand, when we're dealing with mathematics, we are often interested in ordered pairs, and we use these nice brackets on the x and y to indicate that you are dealing with an ordered pair where the order now matters. So xy would be different from yx. And in axiomatic set theory, that turns out to be just shorthand for a nice pair set. So from the pair axiom, we can form the following set. It's the set consisting of x and then the set of xy. So that would be applying the pair axiom essentially 2 times in a row. And here, that would be the definition of the ordered pair xy. And you can continue doing on sort of a similar setup to form ordered triples and ordered 4 tuples and ordered 5 tuples where the order matters. Now, if we fix some domain of objects in a first order language, maybe think something like in Tarski's world where you have a bunch of shapes and blocks, and a predicate p of xy that is binary, we can model the properties of P using a set of ordered pairs. And the way that it works is you look at the set of ordered pairs XY that basically make the predicate true. So when you plug in X and Y, it turns out to be true. Here we haven't seen the notation D, but that just means the collection of all ordered pairs where X is an element of D and Y is an element of D. This relation, which I've labeled with an R, turns out to be what we'll call the extension of our predicate in our domain of objects. So in other words, in some sense, it's the set of objects in our domain that make the predicate true. Now, we'll see a really nice sort of example of this when we look at first order structure through the lens of Tarski's world. But for now, the extension is just the set of ordered pairs that make the predicate true when you plug in that x and y to the predicate. And even though it's only talking about sort of ordered pairs here, this is also true for 3-ary and 4-ary and 5-ary predicates, where you look at not ordered pairs, but ordered triples and ordered 4 tuples and ordered 5 tuples and so on and so forth. So you can also define a relation for the extensions of those predicates as well. The textbook leaves out the representation of functions in a first order structure because, as they pointed out in previous chapters, it's always possible to rid your language of function symbols in favor of predicates. However, since some of our most interesting languages will include function symbols, like the language of arithmetic, I've included here a bit about functions and how you represent them just the same way that you might represent a predicate using a relation. So here, again, we're going to fix some D, which is a domain of objects in a first-order language. And you can think of maybe like when you're constructing a world in Tarski's world, the set of actual blocks or bricks that might be appearing there. And we'll let little f be a 1-ary function symbol. And that's just for sort of clarity here. But you can work with an n-ary one as well. It just means that you'd be working with not an ordered pair, but an ordered n-tuple. And we can model the properties of our function symbol using a set of ordered pairs. And in this case, we will represent it not with a relation R, but an actual function, which I'll call capital F. And it consists of those ordered pairs in D cross D, so ordered pairs from this domain D, with the property that when you apply the function to x, you get back this value of y. And in mathematics, this set of ordered pairs is often called the graph of the function. So, for example, if you were looking at a function from the real numbers to the real numbers, this collection of ordered pairs would be the literal graph of the function itself. Down below, I have included the definition of the domain and the range of that particular function. But the idea is, again, that we would take our one-ary function symbol and represent it using a honest-to-goodness function in the domain. And again, this works not just for one-ary function symbols, but for n-ary function symbols. So basically any function symbol that we would like. Now on the next slide, we'll introduce the notion of the first-order structure, and we'll omit the notion of function symbols from the definition. But later on, we'll come back and say a bit about how we might incorporate them into an example, and we'll sort of reference this slide that you're seeing here. So we're now in a position to define the notion of a first-order structure in set theory. And the reason we need to introduce first-order structures is that they play the same role as truth tables did for propositional logic, but now in the setting of first-order logic, where we're introducing and eliminating quantifiers in our proofs. Now, when we go on to prove the completeness theorem and the soundness theorem for first-order logic, when we do that, instead of referencing truth tables, we'll have to reference these first-order structures to understand the semantics of our sentences. Okay, so the definition here is fairly technical, and once we go through the definition, I'll give two examples of actual first-order structures, one that arises from Tarski's world and another that looks at the language of arithmetic. Now, the first thing that you should notice in this definition is this strange-looking symbol. In this case, that's an M. And the font that you're looking at is a Fraktur font. And it's typical in logic to use Fraktur letters to represent first-order structures. So that is an M, and you'll hear me reference it as an M for the remainder of the video. Okay, so a first-order structure is actually a function. So that M is denoting a function. And the domain of the function turns out to be the predicates of the language, the universal quantifier from the language, and the names of the language, or basically the constant symbols in the language. Now, it's not included here that there are any function symbols in the language, but as I said with our previous slide, we can modify this definition if we'd like. And once we go through the full sort of 1, 2, and 3 here, I'll say a bit about how we might incorporate function symbols. But the definition that's adopted by the textbook doesn't include function symbols, and so that's what you're seeing here on this slide. Okay, so the M again is a function, and its inputs or its domain are the actual predicates, names, and the universal quantifier. And we'll say that this function itself is a first-order structure if the outputs of the functions for these given symbols in our language have some very specific conditions satisfied. In fact, there are 3 of them. First, when we apply our function M to the universal quantifier symbol, that's that upside down A, what we get back is just a non-empty set. And we'll think about that set as being the domain of discourse of our function M. And there you'll notice that there's a slight typo there, that M should have been a Fraktur M. But that universal quantifier gets mapped to our domain of discourse. Now, the second condition is that if we have an n-ary predicate symbol in our language, Then M takes that predicate symbol as an input and outputs a collection of n tuples. So, for example, if it was a binary predicate, it would output a set of ordered pairs of elements from the domain of discourse. And this is what we were calling the extension of the predicate in our domain of discourse. So for each one of those predicates, it outputs one of these relations. Now, the third condition is that when you apply M to one of our constant symbols, for example, C, the output is just some element of the set D. We call that element the referent of C, and it's what C is naming inside of the domain of discourse D. Now, if our language did include some function symbols, we could then include that in the domain of this function. And when we applied M to a function symbol, what we should get back instead of an extension or a referent would be something like a graph of a function. So similar to what we said in our previous slide. But again, for the official definition that we adopt in the textbook, we'll only consider these first order structures being functions whose domain is the universal quantifier, the predicates, and any constants within our language. Now, the final sort of piece of information that makes it a first order structure is that we're always required to look at the extension of the identity predicate in the same way. It's always just going to be the set of ordered pairs XX for every X in the element of D. In other words, equality really does sort of mean that the two things are actually equal. And that'll make a bit more sense as we go through some examples where we'll look at M applied to the identity symbol and see what the output looks like in that particular case. So let's look at an example using Tarski's world. And let me just point out that anytime you've constructed a world in Tarski's world, you were in some sense constructing an actual first order structure. Now, first order structures will be more extensive than just those you can construct in Tarski's world, but anytime that you built one of those worlds, you were really sort of building up one of these first order structures. So let's look at a nice example here where we have three shapes. We've got a blue cube, a yellow dodecahedron, and then a pink tetrahedron up there in the upper right corner. We've got a constant C that is naming that blue cube. We've got two constants A and B that are naming the dodecahedron, and then the tetrahedron doesn't have a name at all in this particular setup. Now, recall that the number of predicates in the blocks language is fairly extensive. I think there's actually 16 of them. And we'll go through each one of them here, pointing out what information they represent in the picture that we're seeing above. The first thing that we'll look at is our first order structure M applied to the universal quantifier. So again, remember M is a function, and we apply that function to our constant symbols and our universal quantifier symbol and any of our predicate symbols. When we apply it to the universal quantifier, we get back our domain of discourse. And here I've labeled that domain of discourse as a set with X, Y, and Z. Now, at this point, when you're building up a first order structure, you're free to use whatever letters you would like, X, Y, and Z. But I've used X, Y, and Z here just so they don't sort of interfere with the constant terms or any of the predicate symbols that we've already sort of adopted for this first order language. Here, X is supposed to be sort of the representative for that blue cube, Y is the representative for that yellow dodecahedron, and then Z is going to be sort of the representative in the domain of discourse for that tetrahedron in that far back corner over there. So the domain of discourse is X, Y, Z. And again, we were free to use whatever three elements we would like to represent this mathematical structure. But once we identify those and say sort of what they represent in the picture above, the rest has to sort of be fixed. So let's first talk about our constant symbols, which are A, B, and C in this particular language. When we apply our first order structure M to that constant symbol A, we get back Y, which was the element in our domain of discourse that was representing that yellow dodecahedron. Likewise, when we apply M to the constant symbol B, we get back Y as well, and that's because A and B reference the same element in the domain of discourse, in this case, namely Y. M of C gets output as X. And again, in that definition of a first order structure, anytime you have a constant symbol and you apply the function, which is the first order structure, the output is something in the domain of discourse. Okay, so those are our constant symbols. Let's now say a bit about our one-ary relations, and that would be tet, cube, dodec, small, medium, and large. And what we're going to find is that because those are all one-ary relations, the output is just going to be elements of the domain of discourse that make those properties true. So, for example, we were saying that Z is representing that tetrahedron up on the upper right-hand corner. And so M of tet would just be that single Z because that's the only tetrahedron in the picture. M applied to cube would just give you back X because X is the only object in the domain of discourse representing a cube, and that's in that bottom left-hand corner. And then M applied to dodec would just give back Y. Now, all of the shapes that you're seeing in this picture are all small because I haven't changed their size when I introduced them in Tarski's world. And so when we apply M to the one-ary predicate small, we get back X, Y, and Z. Those are the three objects in the domain of discourse that satisfy that particular predicate of small in this case. Now, when we apply M to medium or large, since there are no medium or large objects, we just get back the empty set. So no elements that satisfy medium or large. And then for the binary predicate left of, we should start now getting out some ordered pairs. And here we include the ordered pair XY because that blue cube is to the left of that yellow dodecahedron. And then we include the ordered pair YZ because that yellow dodecahedron is to the left of that pink tetrahedron. And those are the only two relationships that we have here in terms of the left of predicate, or that make the left of predicate true. Now, right of is just sort of the reverse of left of, so you can see that those ordered pairs just get swapped around compared to what we have on the left of. Similar sort of setup for front of and back of. And then for smaller and larger, there are no ordered pairs where one element is larger than another or one is smaller than another because they're all small. So we'll get back the empty set in both of those cases. However, for the binary predicate same size, notice that all three of these objects have the same size. And so what we get back is all the different possible ordered pairs. And in this case, there should be, 9 of them total. And the same thing for same shape here, except for what we should get back in same shape is just the elements XX, YY, and ZZ because each one of these objects has a different shape. None of the objects are in the same row and none of them are in the same column. And so when we apply our first order structure to same row and same column, we get back the empty set. And so you can see that if you had this first order structure, you could sort of build up this Tarski's world example. And if you had the Tarski's world example there up on the top, you could sort of build in this set that you're seeing down at the bottom. Now we're still missing a couple of predicates because we didn't have sort of room for them on this particular side. But on the next slide, we'll finish that up, and we'll finish our first order structure. And remember, we have to have an output for any given symbol within our first order language that's either a predicate, a constant, or the universal quantifier. The three remaining predicates are the adjoins, between, and the identity predicate. Here, since none of the blocks are next to one another, the first order structure M applied to the adjoin predicate just gives back the empty set. In this case, that dodecahedron, which is represented by Y, is sitting in between the cube and the tetrahedron along that sort of black diagonal. And therefore, the ordered triple YXZ would make the between predicate true. So in this case, that would be the only thing that would be true, or the only set of triple that would make the between predicate true. And then finally, the identity predicate has to give back exactly the identity relation, because the only way that two pairs can be identical in this case is if they're actually the same. And so you get back the ordered pairs XX, YY, and ZZ. And this finishes up all of the predicates, constants, and the universal quantifier. And again, you can see how if you had the information about Tarski's world, you could write down this first order structure. And if you had this first order structure, you could then come back and write down one of these Tarski's world sort of files. However, realize that the first order structures are a bit more open-ended because, for example, there's no restriction on the number of objects that you can put in a set. However, in Tarski's world, there is a restriction on the number of blocks that you could put. You couldn't put more than the number of points on the grid and the checkerboard above. So the notion of a first order structure sort of generalizes this idea of a Tarski's world file. Let's now give an example of a first order structure that uses the language of piano arithmetic, or just arithmetic. Here there are three function symbols. There's the symbol S, which is a one-array function symbol called the successor function. And then there's two binary function symbols, addition and multiplication. There's two constant symbols, 0 and 1. And here I've made them sort of bold in the language to emphasize that those are the symbols within the first order language of arithmetic. And then we have two predicates. There's the identity predicate, which is a binary predicate. And then there's this less than predicate that is, again, also a binary predicate. Remember that a first order structure is a mapping from these symbols that are the function symbols, constant symbols, predicates, and the universal quantifier into a collection of sets. So first off, when we apply this first order structure to our universal quantifier, we get our domain of discourse. And in this case, the domain of discourse is only going to include three elements. And here we're free to really choose whatever we would like for our domain of discourse, as long as it's some non-empty set. And if we change that non-empty set, we would change our actual structure. But in this case, we're taking it to be just 0, 1, and 2. So there's three elements in our domain of discourse. Now, when we apply our structure to our function symbols, we're going to get back ordered pairs for our successor function, since it's a one-array relation, and we're going to get ordered triples for our addition and multiplication function symbols here. And basically, the idea is that it's telling you for a given input what the actual output would be. For example, on that first line, that first ordered pair 0, 1 is telling you that the successor of 0 would be 1. The next ordered pair tells you that the successor of 1 would be 2. And then finally, that third ordered pair 2, 0 tells you that the successor of 2 would come back around to 0. So it sort of looped back around. In particular, because of that, we wouldn't satisfy the axioms of piano arithmetic, but nonetheless, we could still form a structure for the language. The triples that you're getting for addition and multiplication here are just addition and multiplication sort of module 3. So for example, in addition, we have that triple 0, 1, 1, and that would represent 0 plus 1 is equal to 1. And then all the way at the end, you have something like 1, 1, 2, and that would represent 1 plus 1 is equal to 2. The same thing is true for multiplication, and you can sort of consider these as just being the multiplication tables or the addition tables for these two operations. We have our constant symbols 0 and 1, and here our first order structure sends those constant symbols to the element 0 and the element 1 in our domain of discourse. And again, here I've highlighted the constant symbols in terms of a bold 0 and a bold 1, and then the elements of the domain of discourse just as a regular 0 and 1. The identity predicate has to be the same in all possible first order structures. So here it's just going to be those pairs 0, 0, 1, 1, and 2, 2. And then the less than relation, in this case, just puts together all those pairs that make the less than relation true. So 0 is less than 1, 0 is less than 2, and 1 is less than 2. And that's all we include in this particular setup. Now notice that this goes through all of the predicate symbols, constant symbols, and the function symbols. And this would be an example of a first order structure. In our next module, we'll show how to talk about satisfaction and truth of sentences based on these first order structures. But for now, we're just giving some definitions of these first order structures and seeing that really we need some axiomatic set theory in order for these first order structures to actually exist and to reason about them.